Hello everyone, welcome back for another session on SS330, Statistics for Social Science. Today we're going to introduce hypothesis testing. And I just want to give you a heads up, I'm recording this in the Olin Computer Lab where they are actively doing construction on the other side of a false wall. And somebody is outside, jamming to some tunes because it's a beautiful day, so you may hear some background noise. So where I need you to start is to log into our classroom page, and you're going to want to scroll down to hypothesis testing. You should be able to see a link that's available now for the notes. And so the first thing I'd like you to do is open up these notes, because one of the things we're going to do today is work together to fill in these notes, and I can also explain to you what you need to know so that you can be able to do your homework number 3 successfully. So this is going to be broken up into 3 separate chunks. The first chunk will cover sort of the background of how do you do hypothesis testing and what is it testing. I'm also going to explain statistical significance and z-scores, and then we'll have a separate lecture for one sample t-test, and then a third one for a difference of means between 2 groups, which is also known as independent sample t-test. I use those 2 terms interchangeably on purpose because you need to know that they're both talking about the same thing. So difference of means between 2 groups is the same thing as an independent samples t-test. Okay, so when you open up the notes, you'll probably find that you are not able to edit it. So the first thing you'll need to do is come up here to File and make a copy. This will allow you to have a document that you can type notes in. And I'm going to say it again because you can't hear it enough. I will be putting some notes in here, but it's by no means what you should limit yourself to when you are typing in your own notes. The more information you give to yourself and the more things that you type into your notes, the more help it's going to be later when you have to be tested on this stuff in your next exam and when you need to do homework number 3. So when you've got your notes open and you've got your copy where you can come in here and edit it, I want to start this conversation by talking about hypotheses. So hypotheses are a little bit different from a research question. A research question, like you just had to do in exam number 1, they've got to have specific things. It's got to have a unit of analysis, a dependent variable, and an independent variable. And these are all good things. Also, an explicit direction and have comparison built in within it. But in a hypothesis, you're getting even more specific. The hypothesis, when it comes to statistics, is the actual mechanism that you'll use to understand whether or not, after you do a statistical analysis, okay, what does it mean? Does my test results support my research question, or does it not support? And the way that you determine the support or not support is through the hypothesis. So the hypothesis is going to look really different from the research question. There are 2 types of hypotheses, and you will always have to specify both of these. The null hypothesis is, here I'm going to type, what you hope to find evidence against. Let's see, we want to reject this. The alternative hypothesis is what we hope to find evidence in support of. We want to accept this. And this is really how we talk about the null and the alternative. So when you think about them as a concept, the null hypothesis is, in one sense, the straw man argument. It is the thing that you set up with the hope of finding evidence against it. When we do a statistical analysis, you're going to get a result. And the result will either give you support for an alternative hypothesis, or it will not reach a high enough threshold, and you basically won't have the support that you need at the critical value that we're looking for, and then you'll be forced to live with the null hypothesis. If you are able to accept your alternative, the language that you use is you would say, we reject the null. The evidence that we found is in support of the alternative, and we're able to reject the null hypothesis. What we're going to do today is not actually in this video will we get into the hypothesis testing with a t-test. We have to start sort of more generic, But in the follow-up videos, you'll see me set up hypotheses and also talk about how do you know you've got a high enough level of evidence that you can reject the null and accept the alternative. So as we've discussed before, when we talk about numbers, we're usually going to have a lot of data that we're working with. And so what we end up doing is having descriptive statistics that give us a sense of like, okay, what's the minimum, the maximum, where's the average, where's the central tendency of the data? And when we get into hypothesis testing, we're going to be using descriptive statistics in order to test our hypotheses. The most common descriptive statistic that we use is the mean. So most of the time what we're doing is we have a group, and that group of data has an average, and we want to see is whether or not there's evidence that supports that average is like the rest of the population or like other samples that we're aware of, or is it not? It's a pretty kind of cut and dry question, even though the process can be, I don't know, like there's a lot of steps involved in doing it. Whether or not you get to accept the alternative hypothesis depends upon statistical significance. Statistical significance is this big fancy term. Anytime someone is talking about statistics or talking about something that's mathematical or they're talking about evidence and they use the word significant, you should always assume that using that word significant means that it's statistically significant. And what that means is that they've essentially found evidence mathematically that supports that what they found represents a broader sample or the true population, depending on the kind of test that they used. In other words, another way to think about it is that the results they get didn't happen by chance alone, that there's actually something there, a real discernible pattern. But big thing to keep in mind, and this is where we start talking about assumptions, none of this stuff happens in a vacuum. Like we assume that if you have data that you're going to use for a statistical analysis, that data conforms to a certain number of basic assumptions. One is that it's a big enough sample size, and that the way that sample was gathered was broadly representative of the broader population. So if you have a biased sample or you have flawed wording and so that your actual data isn't really high quality, when you do a statistical analysis, it doesn't care. Like it's not going to check for those things. And so it might give you results that are really, really misleading. The second thing that it assumes is that you have high quality data and that you're actually measuring things with accuracy and validity. It assumes that, for example, if you ask someone survey questions, that they're going to give answers honestly. If you suspect that there's some real issues or flaws in your data, none of the statistics in the world can correct for that. Third thing that you need to know, and this is something that like really triggers me, it's right up there with pie charts, is that in social sciences, we never prove anything. So anytime you use that P word, you're gonna get like ice cold water running through my veins. Like, please, please, please don't do it. Please don't say that we prove things. And the reason why we don't prove things is because we study people in the social sciences, and have you seen people? People be cray. And so it doesn't matter how big your sample is, how high quality your data is in your measurement, and how wonderful your survey was. People are weird. And anytime you think you have found the absolute causal pattern for behavior, there's always going to be somebody that it doesn't apply for. And so what we say, instead of prove things, is we say we have found evidence in support of, that there is a strong likelihood. We say there's a high probability, but we never say prove. And if you're reading someone's research and they say the P word, you need to automatically be suspicious, because that is just real strong language. It's rarely ever appropriate to say we prove things. Like maybe in law. In law you could prove things beyond a reasonable doubt, but never in social sciences. Okay, so then we're going to come down here to part 2. So the hypothesis testing procedure. It's really straightforward, right? Like you just do the steps and that's it, you move on. So first you have to figure out what is the statistic you're trying to estimate. Most of the time we're going to be using the mean. Once you know what the statistic is, you're going to look at your data and use your data to set up your null and your alternative hypothesis. You're going to run the appropriate statistical test. And for right now, you don't need to worry about what the test is. I will always tell you, run this test with this data. After you run the test, you're going to interpret the results, and then you're going to make the decision. Do you accept the alternative, or do we fail to accept? Are we forced to live with the null? After you make the decision on the hypothesis, then you're going to put your results into context. What does it actually mean? Oh, I'm so sorry, I got a text. I will turn my phone off. Trying to be professional here. It's a real struggle some days. So what this all sort of is underpinned by is this concept of error. And there are two big types of error in statistics. There's type 1 error and type 2. Type 1 error is when you reject the null and you accept the alternative. In other words, you're like, that conventional wisdom, what people thought was happening, I can reject that and I can accept my alternative idea. Like, I have evidence from my data that supports a different narrative. But actually, that's wrong. The null was correct. Type 2 error is the reverse. The type 2 error is when you accept the null hypothesis, but really the alternative was correct. Type 2 error is the overly cautious one, while type 1 is a little bit more like, wishful thinking, you got excited. So if we come down here, I've got this little table, and you might want to add in some information here. But basically what I'm trying to show in this error table is the different types of error. So type 1 and type 2, how do you know when you've made a correct decision versus committed type 1 or type 2 error? And the story I like to use is with pharmaceutical drugs. Because pharmaceutical drugs, I don't know if you guys know about pharmaceutical companies, but these people are loaded with money. I call them people because the Supreme Court ruled not too long ago in Citizens United that if you were a corporation and wanted to spend money, that money was a form of speech, and so corporations are essentially given First Amendment rights, and First Amendment rights are applied to we the people. So, people, corporations, interchangeable. Thank you, Supreme Court. So anyway, you're a pharmaceutical company, and you are, maybe you're working on a new COVID vaccine or a COVID drug that will really help people who are super sick in the hospital. There's a lot of pressure to get drugs out into the marketplace. One, you want to help people, but two, if you get the winner drug out there, you're going to make a lot of money right now. So there's that pressure. There's also the pressure of if you put a drug out on the marketplace too soon and you haven't thoroughly tested it and it actually hurts people, you can just prepare to have lawsuits for the end of time, because people are going to sue to try to collect damages to right for some wrong. This is a huge cottage industry in law, by the way. I don't know, sometimes you'll wander into late night old people TV, and you're there because you're going to see commercials about, I don't know, have you or someone you loved died from taking blah, blah, blah. If so, call this number because you could be entitled to, a settlement or big money. That this is an actual thing when there are businesses that can market on television ads to gain clientele, sorry. So anyway, back to my example. If you are a pharmaceutical company and you're working on a COVID drug, what you want to do is enough testing so that you can put it out before your competitors, but not so little testing that it goes out while it's still dangerous. So let's say in this first block right here, if the null hypothesis would be, don't put the drug on the marketplace, the drug's not safe. It needs more testing. The alternative hypothesis is, no, put the drug on the marketplace, the drug has been vetted, it's safe. If you say that the null hypothesis is that the drug is not safe, you do some clinical trials that show nope, the drug is not ready, and you accept that, then awesome, you've made the right decision. However, if you accept that the drug is actually ready and you decide to reject the null and basically say, yeah, take that drug to the marketplace, you have committed type 1 error. And people are going to take that drug. And some people maybe will do okay, but some people are going to get really hurt and possibly die. This is the one where you get sued. On this other side, if you say, you know what, the evidence comes back and it shows that the drug is not ready, it needs more testing, and you accept that, then you've also made the right decision. But that's this one up here. If you come in and say, hey, I don't believe the data. I think that the null is probably right and we need to do more testing, even though maybe some data shows that it is ready. That's also a type of error. You're being overly cautious. So you're holding the drug back from the market to do more testing, but really the drug is ready to go. And if you released it, people would get better. The other correct decision is when you do the test, evidence shows that the drug is helping people, and you accept that as the reliable data. You reject the null, accept the alternative hypothesis. The drug goes to market, people get better, your company makes $1 bajillion, and you get a $1 bajillion bonus, and everybody wins. And the next thing you know, you're on a cruise ship, probably your own cruise ship in the Caribbean, drinking martinis and living your best life. So that's the error table. So in the social sciences, that decision on okay, do we accept the null or reject the null, sometimes can be, it's kind of high stakes sometimes. Not as much in my work as a political scientist as somebody else's work in public health, but you don't want to make these decisions to accept the alternative hypothesis when the null is true, willy-nilly. You want to be pretty confident. The way that we determine that confidence is statistical significance. And in the social sciences, we have accepted a certain amount of error. Most of the time, we are fine with a 5% error rate. So what that means is 95% of the time, that decision to reject the null hypothesis and accept the alternative is the right decision. But 5% of the time, it's the wrong decision. And really, the null was correct, and we've committed type 1 error. So if we're reducing that risk of type 1 error by 5% or less, we're okay with that in social sciences. In the medical fields, 5% error rate is crazy high, and they would never be okay with that. But they're dealing with a different context. Rarely in social sciences are we talking about people's lives on the line. We're mostly looking for patterns in behavior and dealing with survey data. So I have this picture of the standard normal curve here, and there are a couple of things I want to note here about standard normal. So these are things that are always true about a standard normal distribution, and it can be really, really helpful. One thing is that, come back. I want to type this up here. The mean and the median are the same number. And at the 50th percentile. So exactly half of the data are on the right of the mean and half are on the left. So the value of the mean exactly splits the data. That's how you can see here, it goes right up to the tippy top of this hill. What you see, the numbers below, is the standard deviation. So from one standard deviation out on either side, you get over 60% of your data. 2 standard deviations out, you've got 90% of the data, and by 3 standard deviations, you've got 99% of your observations. So in a true standard normal, because 50% of the observations are on either side of the mean, the area under the curve sums to 1. Let's say there's 0.5, 50% to the left and right of the mean. Not the man, but the mean. There we go. Let me fix my spelling error. This is super helpful when we're determining statistical significance, because what we will say is, hey, you know what? If the null were true, what we would expect, if this is the true distribution, we would expect to get a value close to the mean, right here around the tippy top of the curve. But if the null was not true, how would we know? Well, we would know if we get an unexpected result. So if we get an answer that's down here in the tails on either side, that's evidence that maybe there's another distribution. So again, if the null were true, if it was the correct distribution of the data, we would expect an average that was close to the average of this null distribution, or this theoretical distribution here. But if the null distribution, if this distribution here is not true, if there's another distribution that's more accurate, we would get a result that's in the tails, right? Because The true mean, if it's in support for the alternative, is not going to be what the distribution of the null looks like. It's going to be of some other distribution. So if we get a result out here in the tail, that's going to be pretty surprising. It would be unexpected if the null were true. And so that's what we use for, that's how we determine statistical significance. Statistical significance basically means you were getting a result out here in the tail, and it then is evidence that there is another distribution that's more accurate, i.e. the data that you're using. When we get into the actual statistical analyses and we get results spit out to us, they are going to give us these results in terms of p-values. So if we get a p-value, the p stands for probability. If we get a p-value that is 0.05 or smaller, that equals statistical significance. Spelling is hard. And what that's referring to is where in the distribution are you likely to see that observation. If we got a p-value that was bigger than 0.05, let's say it's 0.10, it would mean 10% of the time you would, when you reject the null, you would be making the wrong decision. Essentially, it's saying that your distribution or your findings are like, they're not out here in the tail, they're closer in here. And so it's increasing the risk that rejecting the null would be committing type 1 error. 0.05, the reason why we use that is a 5% error rate. It means that only 5% of the time would you be rejecting the null hypothesis, and that would be the wrong decision.